All right. Well, I was responsible for the notes for 15.2. I'm covering definitions 15.2 and theorem 15.2 as well. So we're going to start with definition 15.2, and I made this notes file so that you can follow along with me kind of as close to what we would do in a normal class as possible. So if you wanted to even fill some of this in before we get started, you're more than welcome to. Just going to go ahead and jump straight in there, and since I can't call on people to fill it in, I'll go ahead and fill it in for us. So starting off with the continued fraction made from a sub 0, from a sub 1, all the way up to a sub n, by cutting off the expansion after the kth partial denominator of a sub k, is what's called the kth convergent of the given continued fraction and is denoted by c sub k. In symbols, what this is referring to is that c sub k would be the continued fraction of a sub 0 from a sub 1 all the way up to a sub k, where k is strictly between 1 and n. And that is inclusive, actually. So I said strictly. What I meant to say was that it is inclusive between 1 and n. And we'll talk about some special cases where it might be a different value. For instance, if it's the 0th convergent, c sub 0, we're just going to let that be equal to the number a sub 0. Okay, just a side note here, and this will be an important one for our theorem later on, which is that if we have k less than n, and if a sub k is replaced by the value of a sub k plus 1 divided by a sub k plus 1, then the convergent c sub k will become the convergent c sub k plus 1. In symbols, what this would be saying is that if you start with a continued fraction of a0 from a1 all the way up to a sub k minus 1, followed by, in place of a sub k, if you rewrite it as a sub k plus 1 over a sub k plus 1, this is actually the same as our continued fraction a sub 0, a sub 1, all the way up to a sub k minus 1, a sub k, and a sub k plus 1, which is the same as c sub k plus 1. Also, it's just worth noting that the last convergent c sub n will always just equal the rational number represented by the original continued fraction. Okay, so to give you an example of this, let's go ahead and find the different continued fractions of c0 up through c4 for the rational number 19 over 51, which we already know can be expressed using the notation of 0 followed by 2, 1, 2, and 6. Okay, so c sub 0, that one should be pretty easy. That's just the same as a sub 0, which is the number 0. For the next one, we're going to take c sub 1, which is the same in notation as 0 colon 2, which would be taking 0 plus 1 over 2, which is just 1 over 2. For c sub 2, then, you would just expand your continued fraction by one place, so you'd be going 2 and 1. That would be taking 0 plus 1 over 2 plus 1 over 1, which actually works out pretty nicely to just be 0 plus 1 over 3, which is just 1/3. C sub 3 gets a little bit more complicated. The notation, though, is pretty familiar. So you're going to be using 2, 1, and 2 for this continued fraction, which then would be written as 0 plus 1 over 2 plus 1 over 1 plus 2. So then simplifying this, at first you would have had 0 plus 1 over 2 plus 1 over 3, which then becomes 0 plus 1 over, and then you end up with 8 over 3, which then just becomes 3 over 8. And then obviously for C4 you could do the same thing, but we already know that that ends up being 19 over 51. Okay. Now, one kind of thing to note about this is that besides the last convergent, that these numbers that you get these different continued fractions will alternate above and below this value of 19 over 51 until you actually reach that value. So if you were to plot those on kind of an XY coordinate, then you would start at 0. Your next value at 1/2 would be somewhere up here. And then 1/3 of that, so if we're talking in terms of 6, 1/3 would be somewhere right here, 3/8 right here, and eventually you get to the actual value of C4, which is somewhere in between each of those respective values. Okay, so to give us a little bit more notation to work with, especially in regards to our theorem that we are going to develop, we're going to define a couple of new numbers, which are going to be P sub k and Q sub k, where k will be a number from 0 up to n, as follows. The first term, P sub 0, will just be the same as A sub 0. The next term, P sub 1, will be found by taking A sub 1 multiplied by A sub 0 plus 1, and then P sub k being equal to A sub k multiplied by P sub k minus 1 plus P sub k minus 2. So notice that the kth term is defined recursively based on the previous terms. In a similar manner, let's define Q to be Q sub 0 equal to 1, Q sub 1 equal to A sub 1, and then recursively we'll define Q sub k to be equal to A sub k multiplied by Q sub k minus 1 plus Q sub k minus 2. Okay, so let's go ahead and find a few convergence for A sub 0 up through A sub n. In fact, we're going to find the first 3 convergence starting with C sub 0. Now C sub 0 is pretty easy. We already know C sub 0 is equal to A sub 0, but kind of a convenient way to rewrite that would be to write it as A sub 0 over 1, where notice that A sub 0 is the same as P sub 0, and that Q sub 0, or 1 is the same as Q sub 0. And so what that does is it gives us kind of a nice little value here where we can define C sub 0 to be the same as P sub 0 over Q sub 0. Okay, let's find out what happens when C sub 1 is calculated. So C sub 1 would be the same as taking A sub 0 plus 1 over A sub 1. Okay, so then multiplying A sub 0 by A sub 1 over A sub 1, getting your common denominator, you end up with A sub 0 multiplied by A sub 1 plus 1 all over A sub 1, which you might be able to recognize the pattern starting to maybe, which is that the numerator, A sub 0, A sub 1 plus 1, is actually the exact same as P sub 1, and that the denominator, Q sub, or A sub 1, is the exact same as Q sub 1. So let's go ahead and continue with this. Let's see what happens when we get to C sub 2. So C sub 2 would be defined as A sub 0 plus 1 over A sub 1 plus 1 over A sub 2. So then to calculate this, let's start by finding a common denominator within our fraction. So multiply by A sub 2 over A sub 2. That gets us to the point that A sub 0 plus 1 over, we now have a common denominator, so we can combine our fractions, A sub 2, A sub 1 plus 1 all over A sub 2. Then we can take reciprocal of that, so A sub 0 plus A sub 2 over A sub 2, A sub 1 plus 1. Now we need to get a common denominator for our two terms. So now we'll take our first term, A sub 0, and multiply by A sub 2, A sub 1 plus 1 over A sub 2, A sub 1 plus 1. Ran out of room there, so multiplying both numerator and denominator by that value. So what that gets me to, when I go ahead and multiply that out, is I'm going to end up with A sub 0, A sub 1, A sub 2, plus A sub 0, plus A sub 2, all over the common denominator, which is A sub 2, A sub 1 plus 1. And then for convenience, what we're going to do is we're going to take out or factor out the A sub 2 from our first and our third terms. So that would look like this, A sub 2 multiplied by A sub 1, A sub 0 plus 1 plus, and we aren't going to factor anything out of a sub 0, so we'll put that to the right of the parentheses, all over a sub 2, a sub 1 plus 1. Now this one's probably not going to be as immediate because we never did calculate p sub 2 or q sub 2. So let's go ahead and do that right now. So to calculate p sub 2, that would be to take a sub 2 multiplied by p sub 1 plus p sub 0, where p sub 1 we had already calculated to be a sub 1 multiplied by a sub 0. So a sub 1, a sub 0 plus 1. And p sub 0 we'd already calculated to be a sub 0, which you may notice is actually the exact same as the numerator. So denominator, you can probably already guess what's going to happen, but we'll go ahead and calculate it as well. We can define q sub 2 recursively to be a sub 2 multiplied by q sub 1 plus q sub 0, which we'd already found q sub 1 and q sub 0. Q sub 1 was the same as a sub 1, and q sub 0 was the same as 1, which is the same as our denominator. So in other words, c sub 2 can simplify to just become p sub 2 over q sub 2, which leads us to a possible conjecture that we're going to have. Let's conjecture that c sub k, so for any k, we can write that as p sub k over q sub k, so long as k is between 0 and n, and those are going to be inclusive bounds, which actually is going to lead us into our theorem that we're going to prove, which is theorem 15.2. So here's what theorem 15.2 says. It says that the kth convergent of the simple continued fraction of a sub 0 from a sub 1 all the way up to a sub n has the value of c sub k equal to p sub k over q sub k, with the same bound as above, being that k is between 0 and n inclusive. Okay, so let's go ahead and prove this. And this is going to be a proof that's going to be done by induction. So in our induction proof, for the base case, actually isn't too bad. We've already shown that it's true for the values of k equals 0, 1, and 2 in the above example. So those can suffice for our base case. So then we can go to our induction hypothesis. So our inductive hypothesis would then be that it's true, and since we've already used n, I'm going to say true for the mth case. In other words, it holds that c sub m can be written as p sub m over q sub m. Now I'm going to write that in the kind of more recursive manner, which is that p sub m would be the same as taking a sub m multiplied by p sub m minus 1 plus p sub m minus 2 all over a sub m multiplied by q sub m minus 1 plus q sub m minus 2. Okay, and then our goal is going to be to show that this is true for the m plus 1th case. So eventually we'll want to show that it's true for a sub m plus 1 multiplied by p sub m plus p sub m minus 1 all over a sub m plus 1 q sub m plus q sub m minus 1. So that'll be kind of our goal that we're going to be working towards. Okay, now first thing to note is that the integers p sub m minus 1, p sub m minus 2, q sub m minus 1, and q sub m minus 2 are independent, so are independent of a sub m. Notice that they're dependent on the different denominators, or the partial denominators, of a sub 1 all the way up to a sub m minus 1. So what that means that we can do, and this is kind of an important step in this proof, is that the equation from above, where we defined c sub m, still holds if a sub m is replaced by a sub m plus 1 over a sub m plus 1. Okay, so what that means that we can do, let's go ahead and rewrite our equation from above using that notation, is that we can say that p sub m over q sub m, well, not p sub m over q sub m, but that a sub m has been replaced, so we've got a sub m plus 1 over a sub m plus 1 multiplied by p sub m minus 1 plus p sub m minus 2 all over a sub m plus 1 over a sub m plus 1 multiplied by q sub m minus 1 plus q sub m minus 2. Now, here's the tricky part of that, is that when you make that replacement of changing your a sub m to a sub m plus 1 over a sub m plus 1, we change cm to being c sub m plus 1. And that was by the definition we mentioned at the beginning of this video, which is by definition 15.2. So there's where the definition comes into play in our proof. The next part just involves a little bit of algebra. So what I'm going to end up doing is I'm going to multiply both the numerator and denominator by a sub m plus 1. Now I'm just going to show you it for the numerator because it'll work the exact same for the denominator as well. So you're multiplying that by a sub m plus 1 over a sub m plus 1 multiplied by p sub m minus 1 plus p sub m minus 2. And so when you distribute that, I'm going to go ahead and distribute that to both of these terms first. So that gives us a sub m plus 1. Here that gives you plus 1. All of that in parentheses multiplied by p sub m minus 1. And then you also have to distribute it to the p sub m minus 2. So plus a sub m plus 1, p sub m minus 2. Okay, I'm going to go ahead and continue to distribute this out. So I'm going to take a sub m plus 1 and distribute that to p sub m minus 1. And then we'll distribute the 1, so that's just a plus p sub m minus 1 plus a sub m plus 1, p sub m minus 2. At which point we're looking for some different things that we can do. In this case, we can actually end up factoring out the a sub m plus 1 from your first and third terms. So if you factor that out, a sub m plus 1 multiplied by, in parentheses, a sub m, p sub m minus 1 plus p sub m minus 2. And then notice that we're still going to have a p sub m minus 1 that's out here that's not got an a sub m plus 1 that can be factored out. Now, doing that same process for the denominator will get you the exact same setup, just with q's instead of p's. So you'll have a sub m plus 1 multiplied by a sub m multiplied by q sub m minus 1 plus q sub m minus 2, plus outside you'll have a q sub m minus 1. Now here's kind of the key step, is that now if you notice, what we've got in the parentheses here in both our numerator and denominator is actually the same as our inductive hypothesis. So what we can say is that by our induction hypothesis, let's go ahead and get rid of that real quick. It doesn't want to go away, darn it.